Hola guys, how's it going? Today I've got a pretty good treat for you. So this is a circuit that I was interested in building. It's a piece of test gear that would be that might be of some use to you to build. You could do this very cheaply. It's not that difficult to do. Now it's not the most precise instrument, but that doesn't mean that it doesn't have value still. A curve tracer can tell you a lot of things about semiconductors that you just won't get from a digital multimeter. So really, what you need is a couple of resistors. You need a way to have a low voltage AC power source. So you could take a transformer like this. It's got 115 line voltage, 60 hertz. So you can plug this right into the wall if you wanted to. Now, if you do anything like this, you're doing it at your own risk, you know. But you want to add a fuse in here, obviously, if something goes wrong, so you don't burn the transformer up. But then you just go to this resistor network right here, and this is a 470 ohm resistor. This is a 100 ohm resistor, and they are in series with one of the windings on this AC power supply that you hook to this. And so then you have a junction of 3 right here where you have a 1K ohm in parallel with a 100 ohm resistor right here. And that just creates a voltage divider. And the other part that you need is an oscilloscope that can go to XY mode. So normally with an oscilloscope, the x-axis is going to be a time axis and the y-axis is going to be a voltage axis. And we can see that here. Now the camera is going to pick this up really crappy probably, but essentially I have this across this AC line right now. So if I move this back to default and out of XY, then you should see the sine wave for the from the power supply there. What I've done here, just for those of you that are curious, is I have hooked this up to this power supply right here. And it's current limited. It's isolated from the grid. Now, it's technically not right now because I have my scope grounds hooked up. That's one thing you have to be very careful with. But if anything goes wrong, I can go anywhere between 0 and 120 volts on this outlet. And also, if something goes wrong and I short the output, those light bulbs will get super bright for me and let me know that, I need to address something. And at this low of a voltage, it's not going to hurt this transformer if I short it out and create the circuit with those light bulbs. So you really want something like that. Now, I have to take special care not to twist that variac at all when I'm doing this, because I could put 120 on this, and if you came across that, that would be a bad day. So just, you have to take care with these things and really know what you're doing before you do this kind of thing. So let's go back to XY mode, and you can see that it's drawing a trace. Now, what this circuit really does is it's replacing, since you're in XY mode, channel 1, the input from this probe into channel 1 is going to drive the horizontal axis. And so it's being driven with an alternating voltage right now. It's a 60 hertz sine wave at 8.48 RMS. And so what that's going to do is that's going to cause the trace to start in the 0 point at the middle, then it's going to draw out this way, then it's going to draw back this way and draw back this way and oscillate back and forth like that along with the voltage. So this x-axis is now voltage. Now, the reason this is a purely horizontal right now is because the y-axis is looking at current. So channel 2 is over here in this voltage divider. So when this circuit starts to draw a load, the voltage is going to drop on this Y. And what that's going to do is that's going to cause the trace to go down. Now, if you wanted to do it, technically when your current goes up and it's actually going down, which is a little confusing here, you could put some sort of inverting amplifier in there to flip that up if you wanted to. I don't feel like doing all that and having to get a DC power supply involved, so I'll probably just leave it like this for now. It's good enough to just show you guys how it works. So Yeah, like I believe I said this before, but where this thing really shines is testing semiconductors, diodes, transistors, because it basically draws out the IV characteristic of that semiconductor. You can also somewhat identify Zener diodes with this. So Zener diodes, you know, they're notorious because it's difficult to figure out what their Zener voltage is. Just you can't tell that just by looking at the glass casing. And also sometimes they get confused with like a Schottky diode, because sometimes they put those in a glass case like that. So it's good for component identification. I saw a video where Mr. Carlson's lab hooked his up to a generator, and he was able to see the closing of the breaker points, which brings me to my next thing here. So the most basic test you can do with this is a continuity test. And essentially, whenever you have an open circuit, let's go ahead and snap some leads on here. So we'll put our, since this is connected to the probes, which are going to the ground here, I'm just going to put this in here. And just take care not to come across anything live with this because this is grounded. And then on the other side, I'm going to hook this right here. And these are going to be our test leads. Now what happens if we touch them is it's going to sag this voltage as low as it can go, which is going to cause, like, the voltage is no longer going to be swinging there. It's going to remain constant. So the IV characteristic is just complete conductance. So you get a vertical line here, and that's the AC current that's moving back and forth through the circuit. All right, so all the voltage is being traded into current because it's such a low impedance here. So if I touch them, you get a vertical line. You can take them apart. Bada bing, bada boom. And then a resistor. So a resistor, if you think about it, it lies somewhere between a short and an open. So you get a slanted line out of it. So this is a 1K ohm resistor. So I'll hook this lead here. And then I'll hook this one here. And we get a slanted line like that. So let's try a 100 ohm resistor right here and see how it does. It should be a steeper line because 100 ohms is closer to being a short than 1K. So we should get a steeper line out of that one. Now here's where it gets interesting. So, you know, what this is really saying is that the response of this resistor is linear across this range here. And also it's telling us that it's a pretty low ohm resistor because it's almost vertical but not quite. And then it's also telling us that, hey, our voltage is swinging this amplitude and our voltage is swinging this amplitude right here. So it's a very close to a short circuit because our voltage isn't swinging very much. It's just a tiny amount that it is. And then when the current's swinging up and down, it's drawing that trace. And we end up with this nice straight line right here. Now here's where it starts to get interesting a little bit, is we can test capacitors with this thing. And I'll start with this large one here. It's a 22 microfarad capacitor. And we're going to hook it up like this. And what happens with a capacitor before we do this is, let's hook this somewhere so I can talk. So a capacitor, it doesn't follow a linear current IV characteristic. Like these present a phase shift to an alternating current. In an ideal capacitor, it's 90 degrees, but with ESR and everything, it's always a little bit below that. So especially with electrolytics, they have a very high ESR to them. So essentially, the change, like the rate of change in voltage across these two leads is what is going to determine the amount of current that's flowing through this capacitor, you know, back and forth, back and forth. So essentially, with a sine wave, it starts at 0 and it moves to 90, and it moves back down. Like it moves to where it peaks, and then it comes back down, and that's one cycle right there. That up and down return to 0. And the rate of change in the voltage is greatest at 0, and it's also greatest at or no, yeah, it's greatest at 0 and it's 0 at 90. So, you know, when that sine wave is peaking, the rate of change, the derivative of that sine function, reaches 0. And if the voltage isn't changing, this capacitor is not going to draw any current in that moment. And so as the voltage hits 0, that's where the rate of change is greatest in a sine wave, is right there at the 0 point. So I can just show you that if you wanted to. See if we can trigger on this. Oh, come on. There we go. So the rate of change is greatest here in the middle, and then it levels out to 0. Now this isn't a perfect sine wave, but that would be the 0 point right there. You have a rise, a fall, and then a return to 0. So the capacitor, the current that is being drawn from it, will be 90 degrees ahead of the voltage that's across it. It's going to delay the voltage rising. So the current, or the voltage across these two leads, cannot change instantaneously. It takes time for it to do so. It has to collect some electrons on the plate for the voltage to start to react and rise. So it puts voltage behind current. Now a coil like this would shift the current back 90 degrees relative to the voltage, just due to the fact that it stores energy like in a magnetic field and not an electric field like this guy. So that's the long way to beat around the bush, but I just love explaining this stuff. It's just beautiful to me, the mathematics and everything behind it. But so you can see, like, we're putting a voltage across this capacitor, and you can see that it's presenting an impedance because the amplitude of the voltage goes down. So if we move to XY, we can see that our voltage is moving only that far, but we have a circle here now. So I'll show you, kind of explain what I meant there. So remember how the rate of change in voltage is greatest at the 0 point. So that means that this thing will be drawing, like, this is the 0 point right here in the middle. And you can see it's drawing the highest current that way and the highest current that way. So this would be our positive charge and discharge cycle, and this would be our negative charge and discharge cycle. So that's a fairly big value capacitor. Now, this is a 60 hertz power supply right here. So all of these capacitors, depending on their size, they're gonna present a different impedance to this scope, or to the circuit here. And you can see right here, this one has a very wide swing. So the voltage is swinging very widely across it, and the IV is not that high. You know, so it's not drawing that much current, but the voltage is swinging still by quite a bit. So you can tell that this has a larger impedance to the sine wave than that electrolytic capacitor had. And then some of them, like this is an extremely small one. You have to turn the gain up to see this one. So that's completely maxed out right there. So this capacitor has a large voltage swing across it, but it's barely capacitive because it's barely drawing a little current there. Can't even see it when you zoom out. All right. So just playing around a little bit. I need to turn my y-axis up because I just have a line here. The other thing too is you don't want to have the intensity too high. I'm doing it because I'm filming, but you really don't want to have this too high, because especially if you just have a dot in the center of the screen, because it can burn a hole in the phosphors, the CRT can. So you really want to avoid that if you can help it. So we know here we can calibrate this thing because we know this is our max current, right? And if our max current is this, and we have a component that's drawing a portion of that, we can look at the percentage there to kind of make a guess at the amplitude of the current, you know, that it's that's being drawn by the circuit. You could do all those calculations if you wanted to and figure all that out. Yeah, this one here is a little capacitor as well. You can notice as the smaller they get, noise starts to influence the amount of current draw that's being pulled by the circuit. So that's why we get these little ringing patterns that are drawn in here. It's kind of hard to see that from where you're far away and stuff. Camera doesn't quite do it justice, but here's where it gets interesting, because this is a silicon rectifier, rectum fryer diode, as AVE would say. And so let's hook it up forward biased, and we're gonna see like a downfall right here. So you can see like it just falls off the side there, an exponential curve. So at 0 volts, let's turn the gain down a bit. There we go. So at 0 volts, we're not doing anything, nothing. Actually, this is negative, whatever voltage, and it's coming up, coming up, coming up. And then when it hits this, about 0.7 volts, it starts to conduct exponentially more and more current as the voltage rises across it. So one thing that's cool is if you're familiar with electronics, a lot of the times rectifiers are in a bridge configuration where you have like a full bridge rectifier and there's a diode facing both ways. Well, this is what you get when you do that. Let me reverse this. So now these are in opposition to each other, and we'll just get a mirror image on the other side now. Oh, come on. You get both of them like that. So now it's hitting 0.7. If I can get it to stay, good Lord. Yeah, there we go. So now it's hitting 0.7 on both sides, and that's causing it to rise on either side. So this is sometimes this kind of mimics like crossover distortion in an amplifier in a way, which is pretty sick. But the other thing you can do when it comes to diodes is you can compare them to see which one has the lowest cut-on voltage. So if you hook a diode here, and then let's hook 2. Let's do 2 here. And, oh, I did it backwards. Whoops. This is harder than it looks, gents. Bear with me. Now, if I do it to 1, and I touch the other one, you can see, let me zoom in on the scope here. Watch this move when I touch these. See how it moves just that little bit, and it's moving closer toward the 0 point in the middle. So we can tell that the diode that I'm not clipped to, the one that I'm bumping it up against, has a little bit lower of a cut-in voltage than this one. Sometimes, it might be useful if you need a very specific cut-on voltage for your diode. You could calculate all that out by looking at the divisions and stuff. And so then we have, this is a Zener diode, and this is kind of interesting. Now this is a low voltage one. In order to figure out the Zener voltage, I think you would have to step up the voltage a little bit more than this. But watch here. So we'll get this. See how it curves back up right there? So that is indicating that it's that's where it's moving into its conduction zone for like the 3 volts that it's rated for. So it's starting to turn back up. So you can tell that this is a very low value Zener by looking at that. And let's just keep the same settings actually. Let's do this. Hard to see the bias markers in this lighting. Okay, so we'll leave our settings exactly like this, and what we'll do now is we'll hook in one of these silicon diodes again and just make sure that it doesn't have a reverse knee, and it doesn't. You can see that's pretty straight there at the end. Rectifier diodes have a very large reverse breakdown voltage is what they call it. What else can we do? Transistor. So we can we know that this is like, we could assume that this is the base here, the middle one. And then we could take this and go from that junction to that junction. So we know that that's a forward bias now. And let's look on this other pin and see if we have one. We do. So we know automatically that this is going to be an NPN transistor. As far as identifying the base and the emitter, that's on the 6 hash mark. That's on a little bit above it. So it looks like this would be the emitter. The left would be the emitter, the right or the middle would be the base, and the right would be the collector. So let's look at this. That's a 2N2222. Many of you already know the pinout by heart on that one, but you can see right here we were right. Left pin's emitter, middle's base, and right's collector. So you can identify transistors like that and test them for shorts, because a lot of the times when a transistor burns out, it's going to fail shorted or open one. And if you have one that's open, it's just going to be a horizontal line, and if it's shorted, it's going to be a very, very steep line or just a straight line. So yeah, that's my lesson for today.